Our let's say discussion and webinar session today. My name is Andri Setiawan, and this afternoon I'm going to be, let's say, the moderator for this session of discussion. So for this first session, the let's say the main topic is scientific and technical challenges. So we have three speakers, including myself today, who are going to discuss about how to improve the performance of our infrastructures, how to design structures that are resilient, but also sustainable. So the main question would be how to harmonize resilience and sustainability in our current state. So without further ado, I'm going to start the session. So we will have three presentations, and after all the three presenters have presented, we will have like a combined or a together Q&A session after the presentation. And then we can follow that with more discussion with all the audience who are attending today. So our first speaker today is D.I. Peter Gebmeier, a PhD candidate from the University of Natural Resources and Life Sciences, Vienna. Peter research focus mainly on sustainable construction methods, automation, and also reuse-oriented production processes. And particularly, his ongoing research work focuses on development of an innovative, reusable formwork system for structurally optimized concrete members. So on the right side of your screen, you will see the graphical abstract of the talk today. The title of the abstract that Peter would deliver is Towards a Circular and Automated Future in Concrete Construction. And there are three messages that will be discussed. The first thing is about the challenges that we are currently facing in construction industry, including the problems with the climate change, the rise of extreme events, the resource scarcity, but also labor shortages, especially in Europe. We are facing this problem now. And what Peter and his team propose, which is to integrate sustainability, automation, and reuse-oriented prefabrication into a ready product or ready system for concrete construction. And one of the outcome that will be delivered or that will be proposed to tackle the challenges is a structurally optimized prefabricated component using this modular formwork system, but also combining it with digital twin to support the process from design concept to its fabrication. So without further ado, Peter, I will give the stage to you. The stage is yours.
Thank you very much for your introduction and your kind words. I will just share my screen. I hope you can see now the first slide.
Yeah. Yes.
I think someone is not muted, but that's okay. Yeah, thank you for the FIBs. Thank you, Andre. Thank you, Yannick, for inviting me, for having me, and that I'm capable and allowed to share our scientific work to you and having your ideas, your input also on this work, since I think it's a nice environment also to exchange and create something together. For now, it's just for an overview. It's kind of a mixture of the scientific work we're doing at our institute that's led by my professor, Benjamin Kromoser, and our deputy, Sarah Reichenbach. And together we are about 6 people having different topics and doing research on reusing, automation, structure optimization, and especially in general, it's sustainable design for concrete construction. What drives us in our research, as we all know, as you all know probably, is kind of this graphic that you can see here in green. That's the world population. It's rising. In orange, there's the steel production. And also you can see in blue the cement production over the years, how it's developed over the time. So that's something that's is a bit critical seen from our point of view, that we produce more cement. And yeah, as you all know, the CO2 footprint from concrete is not that good. And hand in hand, it goes that the automation and the productivity, especially for construction, goes down. And as you compare it, with manufacturing, or in total productivity rises over the years, and for construction it goes down. So we have huge potential here to have new ideas how we can be more productive, more efficient with our concrete constructions. And what I found recently, it's kind of is interesting that also society changes. I think that's also a good discussion point for later on, maybe, if you're also seeing this from your point of view, that the using periods from buildings is going down and down over the latest years. So we're using the buildings different than our grandparents probably did. So there's a change in society, in public, and that's something we have to adapt to. And what we are doing at the Institute, as you can see it here, we try to have clever designs. As you can see on the left-hand side, there is just by the design of a bridge, you can reduce the amount of concrete enormously. In the middle, you can see topology optimization of beams, maybe. There you can reduce, just by designing it differently, 20% of CO2 emissions. And also using or reusing our stock better. Also, this is something we're doing at our institute here. It's a work package from a colleague of mine. There we just try to renovate and using new slab systems, etc., or reusing our stock. And as we came to this point that we said, yeah, okay, these are good topics, but for reusing, you need maybe a system so people can really reuse these components we're producing. And therefore we come up with the idea maybe with a modular system. So it's like a Lego system, you can build it up and can build it down. So you need a assembly and a disassembly, dismantle building plan, how you do this. And why we came up with this idea? Since we had a survey going on and also an LCA on different ceiling slab systems, columns, and floor systems. And there we came up that reuse potential is super high regarding or compared with recycling. So the GVP goes way further down if you reuse building components. Less you have to say, it's not climate neutral. You can't compare, you will never get this. So there are a lot of topics we can address. So also CO2 storage will be a thing, since also if you reuse, you already need a certain amount of new concrete to fix stuff, etc. But that's something, maybe it can also be solved. If you're interested, I think I linked everything down below if you want to have a closer look. But as you can see here, the potential is kind of huge, I would say. And that said, it needs a holistic analysis of all building components and the construction industry. So therefore, we had a survey going on with 7 stakeholders where they were asked up to 35 questions. And we had over 100 participants, as you can see it here, from manufacturers up to architects to demolition companies, etc. The topics have been about quality of construction components, flexibility, sustainability, logistics, connection types, reuse potential, etc. And there were kind of some interesting outputs about the knowledge of modular construction was kind of okay or high, I would say. But clients, yeah, how should they? They weren't aware of it. But on the other hand, clients, their first and second ranking was sustainability and durability of the building stock. So it's not something like we doing in research. Also, clients want this to happen. For the drawbacks of reuse, you might think architects would say, yeah, the design limitation could be there, they could be angry about it, but no, it's like they also said logistics effort. And as we had then conversations with them, they told us, yeah, sometimes you need some boundary conditions where you can work in them, and then you get sometimes also more creative if you have certain boundary conditions. And then we had some questions about prefabrication or on-site construction. And as you can see here, the engineers preferred the time and maybe also resource efficiency and costs and sustainability. Construction companies have been more like on the left-hand side, but also for precise execution and easier construction. And so they said, and also demolition companies about screen connection would be the best for them because it's more simple to rebuild the building and build up the building. Even though if it's not 100% reusable, the building, as you've seen the potential beforehand, it's also probably worth it to have a certain amount of building components reusable. So our tasks, I would like to show you more from my personal work, how we produce them, how we can automate them, since automation is super lacking in construction industry, especially from my point of view, what I've seen, so Central Europe more or less, and resource saving on several levels. So we can save a lot of in the design at least, and also then having the automation potential for the labor shortage, the maintenance, etc. You just can produce more stable, and also for your health. Don't know how many people of you have been in prefab construction companies and working there. Yeah, it's not that easy, I would say, doing this over several years, working on these, etc. So that's why I came up with the idea with a manufacturing execution system where we use robots to produce these components. But by just producing these components, as we have seen from the survey, logistics will be affecting these components. So that all has to be gathered together in a database where it can be stored. And this is something very important to maintain these database, the information of your products. If they're reused, you can pass them to the next building. Since if you lose these data, this information of these components, we are at the point as we are here now. People could reuse certain components, but since they don't know what material is it, what steel is in there, who produced it, sometimes this data get lost, and so they are not capable of reusing them. And getting these data from already existing older components is very hard to get. So this is a certain point. So why we need this? This is a picture where we produced our beams 2 weeks ago. And as you can see here on the left-hand side, there's the formwork table, vibration table, with a lot of stuff lying around, working on your knees, more or less. Sometimes on the right-hand side, you can see where the concrete is poured with a crane. That's at least a certain amount of automation you have. But it's not the nicest environment to work in, I would say. In summer, it's super hot. In winter, it's super cold in there. That's why we think of the actual state of practice. We would like to have a system that goes up to Industry 4.0 and 5.0, or be ready at least to have no boundary conditions that are not applicable for Industry 5.0. So for prefab, you have several stages with a formwork table that goes through from standard shuttering, individual shuttering, placing reinforcement, concreting, you name it. And we would like to combine these steps all with doing this task with one robot in a production cell. So it's like a modular production cell. So where each robot has its own cell where you produce your components, and afterwards they go in the curing chamber and can be de-shuttered in any other production cell. So it's also for maintenance way easier, it's plannable, and since we have a full digital production chain, you can also simulate these and have a nicer process overall. It's more effective, productivity would increase. And this is compared to a linear process where you have bottlenecks, and if something happens badly, the whole production just stands still. That's some insights from my tests I was doing with our robot, with my formwork system. As you can see it here, it's fully automated at the moment. The first tests are going up. And in the end, I show you a bit of an older video, but you see how this formwork system is performing. In the back, you can see an already cast concrete beam. And on the next slide, I can show you how we scaled it up to an 8-meter full cast beam that will be also implemented this year, hopefully in our new robot lab. So these are the older stages from placing, and then also de-shuttering automatically with the robot. So that's the focus from my side. Therefore, we built up a digital twin where we can all gather the data from energy loss, energy savings, etc., from the robots, movement. And as you can see here on the right-hand side, that's a full cast 8-meter beam, reduction of 22% of concrete and some steel because it's a truss configuration. And I think that's it from my side. Thank you for attending, and hopefully I gave you some input for the discussion later.
Perfect. Thank you very much, Peter, for the interesting presentation. So, as I said before, we will have the question and answer at the very end. So now I'm going to move on to the second presenter. Our second speaker for the session today is Dr. Monica Santa Maria, a postdoctoral researcher from Universidade do Minho, Portugal. She is also a lecturer at the International Master in Risk Assessment and Management of Civil Infrastructure, NORIS, part of the Erasmus Mundus program. Monica research focus is on infrastructure asset management, structural reliability, and risk assessment. And particularly, her ongoing research work is in the multi-climate project aiming to improve resilience, preparedness, and responsiveness of the built environment against multiple hazards, but also at multiple scales. So the talk today is titled Risk-Informed Decision Making for Resilient Transport Infrastructure System. And this presentation will deal mostly with the, let's say, aging of transport infrastructure, environmental degradation, but also the rise of extreme events. And the work of Monica will explore and present an integrated framework for managing transport infrastructure using risk-informed approach that combines Bayesian probabilistic modeling to simulate particularly flood events and uncertainties with machine learning techniques. And the outcome from her research is the framework that provides a robust decision support tool for enhancing transport infrastructure resilience in the face of increasing hazard and limited resources. So, Monica, the stage is yours.
So thank you so much for the introduction, and thank you also, Yannick, for organizing this event and for the invitation. So, as Andrew already said, I work at the University of Minho as a postdoctoral researcher, and today I'm going to present you some of the research that I conducted when I was doing my PhD here at the University of Minho, and it was focused on risk-informed decision-making for resilient transport infrastructure systems. So it is well accepted that transport infrastructure plays a crucial role in the economic development of a society and its welfare. However, in the recent years, there's been a growing concern about how aging and environmental stressors are affecting our infrastructures. And here, particularly, I focus on bridges. And this problem is especially relevant in European countries, such as Portugal, where a large number of bridges were constructed before 1975, as it's shown in the plot. And this means that they have already reached the end of their intended service life. So due to this reason, we are facing an increased repair and replacement needs, and this also is happening under budgetary constraints. In addition, depending on their geographical location, the transport infrastructure is also exposed to one or to several natural hazards, as depicted in this map. And this exposure, in combination with the inherent vulnerability of infrastructures, has led in the past to large economic losses, with flooding causing the largest ones, as is shown in the box plot. So all of these challenges that I have mentioned are exacerbated by climate change effects, which may increase, for example, the degradation rates of infrastructures and also the frequency and intensity of climate-related hazards. So to face this problem, the concept of risk has long been used for decision support. However, understanding the risks in these infrastructure systems is still a challenging task. And this is mainly because there is like a change of interrelated events that need to be modeled to quantify the risks. And this requires like a multidisciplinary research, and which is happening at different spatial scales. So this begins by the spatial temporal modeling of the hazard, the modeling of the performance of different infrastructure assets that are interconnected, then the modeling of the transportation functionality loss in the case of failure of these assets, and finally the modeling of the estimation of the socioeconomic impacts resulting from this functionality loss. And beyond the concept of risk, resilience has emerged in recent years as a key concept for managing infrastructure systems. So resilience is related with how robust is our system to withstand disruptive events, and how this loss of functionality is recovered after the event, which depends on many characteristics, including how prepared is the system and how is its adaptive capacity. So the overall proposed framework to quantify the risks and support decision-making for resilient transport systems is summarized here in this slide through the different components shown in the flowchart. So the first component consists of the implementation of Bayesian probabilistic modeling of flooding events acting on the transport infrastructure. The second component is the modeling of the bridge fragility, accounting for the deterioration effects. The third component is the consequence modeling part, with a focus on the losses due to traffic functionality. The fourth component is the modeling of the optimal recovery after the disruptive event. And the last component is the resilience assessment to support the decision-making process. Since today I'm doing a short presentation about this framework, I'm going to focus on the last three components. So regarding the first, the first component I will address, which is the consequence modeling, we can separate this into direct and indirect consequences. So the direct consequences can be quantified in a more straightforward way, simply as a function of the physical damage that the infrastructure suffer after the extreme event, and they are related with the repair and the rebuilding costs. However, the indirect consequences, since they are related to the loss of functionality in the system, they require a more detailed examination. So in this study, the indirect consequences that we address are those related with rerouting and the loss of connectivity. In terms of the economic consequences to users, the environmental consequences in terms of CO2 emissions, and the consequences to health in the terms of fatalities due to traffic congestion. So these type of consequences are particularly relevant when the transportation network is not redundant, and for example, the failure of one infrastructure asset results like in very prolonged detours or loss of connectivity. So this is the case in the region of Santarém in Portugal, which was the case study that is depicted in the figure. And this is located along the Tagus River, and it has been affected by severe flood events in the past that have led to the isolation of small villages and also several road closures that can extend for 1 or more weeks. So essentially, during normal conditions, all users of the transportation system are minimizing their travel costs and choosing the route that minimizes their total travel time. However, in the case of a bridge failure, indicated here in red as the failure, for example, of Bridge 13, there will be a prolongation of the travel time and distance since the traffic flow is not possible through that link. Then if we compare some traffic metrics at the network level, for example, total vehicle hours travel, total vehicles kilometers travel, and the maximum congestion index, which are shown in the plot, it can be observed that they will increase, thereby increasing the user costs, the emissions, and the fatalities. Moreover, if we have more than one bridge failure, for example, now the bridge failure, the failure of Bridge 20 as well, we can have different bridge failure scenarios that we need to model and that we need to understand what are the different traffic metrics in order to compute the indirect consequences of each of these scenarios. So this process is time consuming. So to assist in this task, a neural network model was trained to predict the outputs from the traffic model for a large number of different bridge damage network scenarios. So the structure of the neural network model is shown in this slide. So basically, the input layer is comprised by the damage network scenario, specifying the state of each of the bridges, if it is survival or failure. Then the number of hidden layers and the neurons per layer was determined through a manual search to enhance the model performance. And the output layer are the 7 traffic-related metrics defined before. So the performance of the model was evaluated by quantifying the mean squared error, and it achieved a value of 0.09. And this performance also can be evidenced in the scatter plots, which reveal a high degree of predictive accuracy. So in this way, the predictions of the neural network model are deemed satisfactory and they can be used to compute the indirect consequences. Also, it should be noted that these indirect consequences accumulate over all the time until the transportation network is fully restored. So that emphasizes the importance of having a rapid and effective recovery strategy, which is the following component of the framework. So the component of recovery modeling basically aims to support the recovery prioritization to minimize the consequences. So essentially, if we have a given damage network scenario, the recovery process can vary significantly depending on several factors, and this will affect the total accumulated indirect costs. So therefore, the idea of the methodology is to determine what is the construction order such that it minimizes the total indirect costs. And this process is achieved by iteratively comparing for each breach how it decreases the indirect costs given the damage network scenario and selecting the one that minimizes the indirect costs the most. And to support this process, the neural network model is used again here to predict the traffic metrics. And the output of the model is then the sequence of repair that progressively reduces the indirect costs. However, there are other factors that may reduce further the indirect cost by accelerating the recovery process through simultaneous bridge repairs, for instance, or having shorter restoration times. And these factors are related to the system preparedness to react and recover from the disruptive events. And they can be described by three main parameters: the idle time, the repair time, and the number of construction crews that are available to perform those restoration activities. So for instance, if a system has a low preparedness, then it means that they will have limited resources for conducting the restorations. So they will take a long time to initiate, which would be the idle time. Then they will take long repair times. And then they will have a limited number of construction crews working concurrently, which will increase the total recovery time. After quantifying all of the direct and indirect consequences, it is also possible to compute a robustness index for each of the damage network scenarios. So basically, this robustness index can be computed as the ratio between the direct consequences and the total consequences. And this index provides like a measure of the degree to which the transportation system can contain or limit the consequence of hazards. So in that sense, this index can be used to define like a breach criticality as shown in the figure, which informs which breach failures will result in very large indirect consequences that outweigh the direct consequences. And it's also possible to identify through this framework the co-occurrence of breach failures that are like contributing the most to the overall expected consequences and that are having a very poor robustness. And finally, it's also possible to investigate like which are the predominant failure modes for the identified critical scenarios. And in this sense, we can target like the mitigation strategies to the specific failure modes and the critical breaches. And the last component of the framework is the integration of resilience for decision support. So the figure displays the typical resilience curve that focuses on the functionality of the system and how it recovers. However, it is also very informative if we look at the generation of the system capacity to reestablish that functionality. And this capacity develops over time, and it is a part, or it comes from the benefits that the transportation system is providing. So under this concept, resilience can be evaluated as a capacity demand problem, where the economic capacity, which is depicted in red, can be considered as a reserve or like a percentage of the benefit that the system is generating over time, which is in blue, depicted in blue. And when we have a disturbance, then there is an economic demand that will reduce my economic reserve, which is shown like the drop in the red curve. So this demand is like the reconstruction expenses of the failed infrastructures at the time of the disturbance event. And if at certain point in time, the economic capacity to restore the functionality of the system is exhausted, which is exemplified here, so we have such a large demand that we don't have enough resources to recover, then we can call that a resilience failure event, which can be assessed probabilistically. So very similar as we do for the structural reliability problems, we can define like an annual probability of resilience failure. So this concept of probability of resilience failure can be used to compare different decision alternatives for managing the infrastructures. And for instance, if we take into account decisions about the annual reliability level of bridges, decisions on the maintenance investments, and decisions on the percentage of benefits that we should save for reconstruction and recovery, and we assume 3 levels like low, moderate, and high for each of these decisions, we can do different combinations between these 3 decision alternatives and investigate their effect on the annual probability of resilience failure. And the results are presented in the figures. And they indicate that, for example, having a low maintenance level have a significant effect on the annual increase of resilience failure probability. These are the highest levels. And while we have high levels of benefit savings, this decreases the failure probability. However, it's also shown that having like a very poor maintenance has a high effect that can even diminish the effect of having savings for recovery. So to conclude this presentation, I have shown how the application of machine learning techniques can help to reduce the computational costs that is required to compute the consequences, to estimate the consequences while maintaining a high level of accuracy. And this facilitates the quantification of risk and also the identification of optimal sequence of repairs. Also, the framework enables a better understanding of which are the failure scenarios that are more critical, so which are the critical infrastructures and the critical failure modes. And finally, it's also shown how resilience concepts can be integrated into the decision-making framework through the concept of resilience failure probability, which allows to compare different decision alternatives. So regarding future perspectives of this work, and also given the topic of this webinar, the idea would be to extend this framework to optimize this replacement and maintenance decision for transport infrastructures by minimizing the environmental effects and enhancing sustainability at both the asset and the network level, while guaranteeing an acceptable probability of resilience failure. So finding that trade-off between both, between sustainability and resilience, and also to include climate change consideration in the deterioration of the concrete bridges, and also in the frequency and intensity of extreme weather-related events. So thank you for your attention.
Thank you very much, Monica, for the very interesting presentation. So now I'm going to the third presentation. So yeah, I'm going to basically introduce myself here, but I have a PowerPoint. Yeah, my name is Andri Setiawan, and I'm a postdoctoral researcher at Universidad Politécnica de Valencia in Spain. And my main research focus and includes structural robustness, concrete mechanics, shear and punching shear, and also earthquake engineering. And currently, I'm working on several research projects, but the one that I'm going to present today, mostly the first one, which is Endure. Endure is ERC Consolidator grant that is led by my professor here in UPV, and the goal of this project is to develop a fuse-based segmentation to arrest collapse propagation in buildings. But also, I'm working on another project on the ERC proof of concept, which is basically transferring the fundamental understanding that we gain from this main ERC grant to application in practice. So the topic of presentation that I'm going to deliver today is I call it lizard-inspired building design. Let's say to prevent catastrophic collapses. And as has been discussed by the two previous speakers, our problem now are mostly coming because of the increasing of extreme events, either by climate change or also anthropogenic hazards or man-made hazards. And this typically leads to damage in the structures that can then trigger collapses. And as later I will explain with some illustration that most of the robustness guidelines that we have in our current guidelines in building codes, in European codes, or even in American codes are mostly relying on what we call as continuity. So in your system, you need to have a continuous system and redundant system so that if one element fails, you can redistribute and etc. But there are some limitation of this current approach that can actually lead to more severe failures. So based on what we learn from nature, I'm going to explain how we learn from lizards and how we implement it in our building design. So I'm going now to share my presentation. So yeah, just a very brief introduction about our research group here. Our research group is named Building Resilient. It's led by Professor Jose Adam from UPV. We are mostly working on two main research topics. One is on the robustness level on bridges and buildings, but also on structural health monitoring and assessment for infrastructures. So currently our team is quite big. We have 5 postdocs and about 8 or 9 PhD students working on many different projects. But the one that I'm going to present today is specifically about this ERC project. But yeah, just to give you an overview, um, I would say we are quite an experimentalist and we like to do large scale testing. So we have done many experimental tests in the past. For example, here we did some masonry arc fault testing. This is a type of structural system that is mostly adopted for Gothic cathedrals, for example, in Europe. And also here in the middle, we have the opportunity to actually do a testing on a real bridges that is 100 years old. This bridges was extracted from the field and they want to replace it with the new one. So we had the opportunity to test this 20-meter span bridges. We cut some pieces of this bridge and we also did a let's say the cyclic test, fatigue testing of these bridges. And then another one on timber structures, we evaluate some robustness of timber structures. And the two below is two full-scale buildings on flat slabs and also precast. And this is the scale down of bridges that you saw in the middle. So I'm going to be quite short here about the background, which is already being discussed by the two previous presenters. We have the increase of extreme events that actually cause more and more losses in terms of casualties, but also economic losses. But at the same time here, this is like the newest Global Risk Report 2024 produced by the World Economic Forum. And we can see that here we have also total armed conflicts, or we can say geopolitical tension caused this. And you can see that the total armed conflict almost doubled during the last decade. And the fatalities caused by these conflicts almost quadruple or increasing 4 times. So these extreme weather and anthropogenic hazards can typically lead to some damages in the structures, and then depending on how robust a system is, this damage can be localized, but in the worst case scenario, this local damage can propagate to the rest of the system, creating like a domino effect that we call as progressive collapse. So we have seen this in many occasions in the past. One of the first infamous one was in Ronan Point in London in 1968. It was the first incident that actually becoming like the alarm for the engineering community to work on robustness guidelines. And then we see another incident in Seoul, in Sampung department store. And in the same year, we have the terrorist attack bombing in Oklahoma. And the most recent one in Champlain Tower South that happens 4 years from now. And this is just we love to play with Mola kits that we have, and we create some videos on how to illustrate progressive collapse. For example, here you have some overloading in the buildings and some local element fails. And what happens is if the system is not robust, then the failure will propagate. So now the question is when failure propagates and when failure is not propagating, right? Okay, so I'm going to start by, let's say, explaining what we use in current design approach. What we use in current design approach is relying on redundancy and continuity. The idea is very logical and makes sense, no? Basically, this is a mountain climber, and you see, I'm not a mountain climber myself, but if you love doing mountain climbing, you have a safety rope that connects people in your group, no? And the idea of this safety rope is basically to help if one of the party members in your group fails, the other can actually help to sustain the people, to hang the people, no? And this system basically is the one that we have in our buildings, in our reinforcement, in our beams and slabs. So basically, if one local element fails, you can redistribute the loads and then you can prevent failures. So this philosophy has been proven effective in many situations. This one is the building in New York just beside the World Trade Center during the 9/11. And you can see that although the facade was completely destroyed, thanks to the continuity, you can actually prevent major collapses. Also here, the bottom one was a building that was damaged by some missiles during the war in Ukraine, and you can see that the building survives with these new alternative load paths that can develop, right? But we start this project by criticizing actually that this philosophy doesn't always work as we want. Imagine that if you now work in a Mount Everest and your group has, I don't know, 20 people in your group, and it's not just one people that falls down to the cliff, but imagine that 5 or 10 people, half of the group falls down. What happened is actually through this continuity, you can pull the rest of the people, all of them fell down. No? So instead of having 10, you basically pull all the 20. And in this scenario, of course, this is the worst case scenario that we don't want to have in our group. But in this worst case scenario, probably the only solution is to cut the rope, which is basically, okay, you sacrifice in a way some parts, but to save the rest, right? So this is the same. In buildings, if you have this extensive continuity, this is a video showing building implosion that is basically used by people who are doing demolition. And you can see here that you just need to explode, you just need to put some explosion in the middle of the building, and by the continuity, the building can actually just propagate by itself and then it collapses, no? And we also perform some modeling and we actually can simulate the same thing. So if parts of the building falls down, actually through this continuity that is supposed to protect your structures can actually create like a boomerang effect, and actually it creates a larger collapse. So this is the starting point of our project Endure. So what we do, we try to find an inspiration from nature, because nature has been through evolution for thousands of years, and we can see here in lizards, they have the ability, what is called autotomy, to shed their tails or to cut their tails to escape predators, right? So this mechanism is deliberate. This mechanism is not happened by accident. This mechanism is by design. So I will show you in the next slide. There is a very nice paper that is written in Science about how lizard actually breaks their tails, and they have a special segments between the body and the tails that actually can be activated when the lizard moves in some degree of freedom. Let's say if you just move in one directional, the tail will not break. But then if you want to activate the separation, the autotomy, the lizard just need to make some, like a twisting movement, and the tail will break by itself. So what we learn from this is that this mechanism is something that you can engineer. It's not something that happened by accident. So what we do is we try to combine the two opposing concepts that people always think that it's impossible to do because they are both extremes, to have continuity, but also to have segmentation in the same building system. So what I mean is that if there is no extreme event, if there is no significant damage in your structures, you want to remain continuous. You want to remain the continuity because you want to have the structures that are redundant and also have the ability to redistribute the load. But then when there is a worst case scenario, we call it the black swan event, that is very significant or very, let's say, detrimental event with a very low probability of occurrence, we sacrifice some parts of the building to save the rest. So this is what we call as fuse-based segmentation that is inspired by lizards. So in order, of course, we did a lot of simulation, we do a lot of consequence analysis also, but due to the limited time, I'm going just to show you the most interesting part, I would say, which is the validation, right? Because you can have a very beautiful theory, but if it doesn't work in reality, it's useless. So we basically constructed this full-scale building. It is 12 meter by 15 meter in span, 2-story buildings made of precast system. Initially, we create like two conceptual design of this building, design H and design C. Design C is basically original design that is following precisely the conventional robustness design that we have today. And then this is the new proposal that we have, which is the called fuse-based segmentation design. And we want to see what happened and when these two designs are subjected to same failure scenarios, right? So the key here when we design this fuse-based segmentation design is that we design this column and this connection. We use a partial strength connection with a dowel bars that basically functions like a fuse in electrical device. So when excessive forces is being transferred from this horizontal floor system to the column, these dowel bars will actually break, and then it will stop the transmission of forces from the floor to the columns. And by just doing this, we can actually achieve the segmentation as in lizard's tail. So for example, if you have a small failure, these two designs, they behave more or less similar. They can have redistribution. That's key factor, because when you introduce this fuse system, you don't want to disturb the ability of the original building to redistribute the load. But then the contrast outcome happens when you subject this building to a larger failure. So when you subject this to 3 column removal failure, you can see here. So in design H, the failure stops in the border where we design, where we engineer. So this is basically the transition between the body and the tails of the lizard. And the conventional design actually propagates the failure. So you can see that buildings that are designed, even with the most updated codes, can actually result in total collapse. So we perform this. This is the building. The images of the building. We have these dowel bars, and then we have these some holes in the columns to pass the top continuity bars. The top continuity bar is important to provide some redistribution under small failures. But then these dowel bars act like a fuse. And this is the time lapse of the construction of the building. We have our outdoor lab facilities here in Valencia to perform our full-scale testing. This is the erection of the precast columns, and then we continued with the precast part of the beams, and then we have the hollow core slabs, and then we cast the topping all together with the hollow core slabs. And this is the, let's say, the boundary condition and the loading protocol that we adopted. You can see here. We put hydraulic jacks here basically to remove the reaction in the column to simulate column failures. And then here we can see all the sandbags. Later you will, yeah. This is the steel column that is basically is a three hinge column that basically can flip and simulate like a dynamic removal in your buildings. And this is the sandbags representing the overloading condition in your buildings. And probably you will ask like why the other part of the building is actually unloaded or not loaded at all, because this is the most critical scenario when you have parts of the building loaded and it falls down. Actually, if you have unloaded part, you will pull everything. So it's more critical to test in this scenario rather than having all the base loaded. So we perform the test in 2 different stages. This is the first stage. In the first stage, we remove these 2 columns. So you can see the 2 columns are removed and the building survives. Here, of course, with some damages and cracking. Yeah, the deflection here is around 6 centimeter or 7 centimeter for 6-meter span. So this is quite significant. And some of the top bars here in the beams are already yielding. But the system is able to redistribute the loads to the surrounding. So from this first stage, we fully confirm the continuity aspect of the building. But then this is the second part. We trigger the failure here, and then it breaks exactly in the location where we want to have the fracture. So you can see this is the drone view, the aerial view of the buildings. And you can see there is like a clear segment border where basically we designed it to segment in that part. And this is the post-collapse inspection. We took some photos from the drone. This is the border that we designed to segment. We engineer this border. And you can see that the dowel and the corbel breaks and also some slips in the rebar actually allows to have segmentation. And also this part. Yeah, you can see that the continuity bars and all the corbels and dowel breaks here. So yes, of course, and we also performed some simulation, and the simulation was actually done before the test because we need to at least predict and understand how it happens, and we achieve a very accurate predictions of the failure. We use applied element method here to simulate the fracture, impact, and debris. And we can see here that we can achieve a very similar response in terms of the segment border and also the failure from inside. Yeah, so to conclude, this concept combines both continuity and segmentation. So in the first phase, we can prove that continuity can happen and prevent failures. But at the same time, when more extreme scenarios happen, the segmentation will take place and actually helps to arrest the collapse propagation. Of course, some damages suffered in the upright part of the building that is not collapsing. But the most important thing here is that you can still perform safe evacuation and rescue of people from the upright building segment. So, yeah, just to acknowledge, the research is funded by the European Research Council and the ELIC and also ASI, which is a software provider. So thank you very much for your attention, and sorry if I took a bit longer time, but yeah, if you have any more things to discuss, feel free. Thank you very much. So now I think we can move on to the discussion or Q&A session. So I would give the floor to the audience here. If you guys have any question to all our speakers here, please do so.
I would have a question to your research also for the collapsed building. It's super interesting to see these videos over and over again. I'm also sharing them with my colleagues because these are very interesting, huge tests you did. But in what conditions was the rest of the building? Was it like you had to tear it down, or would it also be capable of removing the broken part and rebuild it?
Yeah, yeah. Thank you very much, Peter. That's a very interesting question. Yeah. So, um, at the moment, I think the building must be demolished, right? Because this, of course, so this research that we are doing is a very, let's say, fundamental research, no? So at
Yeah.
this point, what we want to achieve is just to segment, right? But of course, if you have some, let's say, higher performance objectives, let's say if you want to reuse or even just replace some parts of the buildings after the collapse, you can actually do so. But of course, you need to limit the damage that is experienced, no, by the rest of the building. Just to give you some information, the rest of the building that is not collapsed, that is still standing, it's severely damaged. Yeah, so the drift goes to more or less almost 2% or 1.5%, which is basically, if you refer to, let's say, earthquake or seismic code, it's like building subjected to 2,500 years earthquake, which is like an extreme event, right? But yes, if this is a larger building, right? If this is a larger building, you can actually save more parts of the building because the degree of damage will be actually more concentrated in the region where there is like if you burn a paper, no, the part that you burn basically is around the segment, so you can actually save and replace the majority of the parts of the building. If you remember, the Pentagon was during 9/11, no, we have the World Trade Center, but also Pentagon was struck by planes, and actually Pentagon was designed by like a segment system. And thanks to this segment, actually you only lose one particular part of Pentagon, and you can actually redo the rebuild of the whole part. So yes, it is possible, but at the moment in our research, unfortunately, we need to demolish.
Nice. Thank you.
Thank you very much, Peter. So yeah, we have Joao.
Yes, so Andre, it was a very interesting presentation, as I was expecting. I was wondering about something regarding the type of building uses that would be most suitable for this type of system. Because unless I'm mistaken, when you segment, you will stop damage propagation, but you lose hyperstaticity. So you will increase for the same type of building design the probability that one of the sections will collapse because you have less capacity for load redistribution.
Yeah.
So I think this is not meant for residential buildings or where there's the risk of loss of life or limbs, right? Where would this be used?
Okay, that's a very interesting question, yeah, Joe. So, first of all, in progressive collapse, we usually classify the propagation into different typology, right? You have what is called pancake propagation, for example, when you have like an World Trade Center, no, which is vertical propagation. For sure, our system will not work for this, no, because it propagates vertically. So our system first is mostly effective for collapse that propagates like a zipper horizontally. So what type of buildings that suits this best is basically like a low-rise buildings that has a large floor area, large surface area. And of course, this is not for residential, but we are mostly focusing mostly on buildings with high, let's say, occupancy rate. For example, I don't know, commercial or even sports stadium or congregation space, basically, where basically you have a higher risk of terrorist attack, for example. But yes, the example that I show you just now is just a precast system, right? And in precast, actually, the challenge is to segment precast is not so difficult because the nature of precast is fabricated. But the challenge is more on how to ensure continuity. So now, in our team, we are going to test another two full-scale buildings. One is steel and another one is cast in situ concrete. So in this case, it is even more challenging to segment cast in situ concrete, right? So yes, there will be some limitation of typology. There will be some limitation of even the geometry. For example, to give you an idea, some buildings with relatively short span, like I don't know, 3-4 meter span, you don't need to do this because it can segment by itself naturally. So what we are working on is mostly for also buildings with large span, where basically the gravity loads are very dominating and it can actually pull the building down. So now we are doing on risk analysis. We are doing cost benefit analysis also to justify what are the most practical segment size and also what are the most typical, let's say, building geometry and typology that is suitable. But of course, this is not for every building.
Yes, and now I'm thinking about something else.
Yeah.
Just another question. Sorry if I'm taking too much time.
No.
Regarding the methodology, how do you do? Do you speak with architects first? How do you define what to study? And then do you start immediately running numerical models? Do you have some step in between?
Yeah. Yeah, that's a very good point. Yeah. So um, at the moment, we propose some, let's say, some framework, right, on how to apply this. But for sure, it's not like a typical design guideline that you can follow like linearly from start to end, because this typically requires also some iteration, right? Because first, when we are working with this kind of robustness design, we are always working with what we call threat independent. So you don't know which part of the building that could fail. It can fail from inside. It can fail from the perimeter. If you have explosion from inside or explosion from outside, logically you will treat the building design differently, right? But we need to consider all of them, right? So we need to take consider of like the envelope of the situation, and then yes, we need to speak with architect, but also building owners, no? Because introducing this kind of segments can increase a bit the cost, right? So we need to be able also to justify, for example, what is the most practical but also economical way to segment the buildings. What is the risk that the client can accept, no? It also depends on the risk profile. If your building is, I don't know, federal buildings, a White House, of course you can design whatever you want with the risk as low as possible. But if you're working with people from, not from from federal, not from the government, of course you need to speak or talk to them about the risk and cost benefit. So yeah, at the moment we don't have a very clear guideline. We are still working on it, but of course it requires a lot of this iterative process with the clients, also architects, and also the other engineers. Yeah.
Thank you. This was all very interesting, so congratulations.
Thank you very much. Thank you very much, Joao.
I think there's a question in the chat.
Yes.
I also have
If
a
you
question, but I don't know how to raise a hand in Zoom.
Yes, please, Ricky.
Can I go? Yeah, thank you everyone for the presentations. I have questions. First for Peter. Yes, Peter.
Yeah.
Thank you for the presentation. You showed some challenges that we have to work on. For example, the labor shortage that we foresee in the future, and also about sustainability of concrete. And then you also showed some possible directions to go. For example, automation in the process in the prefab factory, and also reuse of elements. But I was thinking, what are the challenges there? Can we already immediately say, okay, we automate all the factories, or maybe there's some cost problems? And I can imagine for reuse of elements, there are also still things that have to be solved. So my question is, could you elaborate more for the solutions that you proposed? What are still the things that we as the engineers and scientists have to solve?
I think there are two topics about the automation and then about the reuse. I think one topic, the other one can be solved with other methodology and stuff. For the less automation or the labor shortage we have, it's just it's a cost investment for sure. You have to buy all these special machines, and some precast fabrications already invested probably a few years ago, 10, 20 years ago, in new precast concrete machines, but they are they're doing some stuff, but it's not super automated. They sold it as a full automated, but in the end, a lot of workers have to de-shutter by hand because the gantry crane that moves around and places the formwork is not capable of removing the formwork or also lifting stuff, etc. Is mostly done by hand or by machines and manually surrounded in the fabrication. And as researchers, sometimes we just focus on very small details in doing our research. So that's one thing I learned, is especially that we have to think big and have all these challenges in mind. So we don't have other borders from when we go into prefab, and when we want to sell them our idea, they mostly come up with limitations or why it's not possible. I'm in the position that we try to implement such a production cell in a concrete factory in the next few years. For sure, I have to build it up at first in our lab, and that's mainly cost intensive. That you have persons and machines, and you have to run them all the time, and that's why we also do simulations now, so we can show them it's worth doing it, since you can talk a lot and show one or two beams, but you have to show them a fuel process also with if something gets damaged, if you have to maintain certain stuff, and also you need a person who can operate these systems and knows what's going on. For sure, now you have a lot of sometimes skilled labor in prefab. They are probably more like a bit older already, so in the next 10 to 20 years, it will be hard to get these kind of people who do this work every day.
Okay, so it's costs and also skilled labor for this automation solution.
And it's just placing the robot doesn't solve the problem. It looks good, it looks nice, but operating a robot 100% doing different tasks is very, very stressful, I would say, to work with. Most videos you can see on the internet when robots do stuff, they're mostly doing the same stuff over and over again. But if you have to adapt to different parts and maybe they move a bit because concrete maybe it shrinks a bit, or maybe it swells a bit, the system has to adapt to it always. I would say this is also a challenge.
Okay, yeah, thank you.
I hope this answers
and for the reuse of elements, I'm also interested in what are the challenges there.
From the survey we did, there was especially the challenge since demolition companies don't have mostly a plan or an idea how this building was built up and how it will build up. So maybe we've seen also the videos from Andre, they get teared down, they get demolished because they don't know how to lift these parts and rebuild it again. So, and if you are capable of doing this, so if a construction company won't buy used beams where they don't know how they were built in, and how they came out of an older building. So that's also a problem we're facing at the moment with now existing buildings. That's why we thought about maybe when we produce now more clever in design and production, and you have the data, it's more easy to reuse building components.
Okay, yes, thank you.
Okay, so we have another two questions from Yannick
Maybe
or
Andy, maybe before I ask my question, there is a question in the chat
okay,
from
okay.
Ali. Maybe first you can
Yes.
ask him because it's been a long time he read
Okay,
the chat.
sorry. Yes, Ali, thank you for the one. My question is what FEM software did you use for the column removal scenario? Okay, so thank you for the question, Ali. For the software that you see in the presentation, it's called Extreme Loading for Structure, ELS, which is basically on applied element method. So this is typically used if you want to simulate like a fracture, free fall, and also debris. But we also combine other with other software, yeah, like even finite element, you can also simulate some removal. But depends if you want to simulate the whole like segmentation and also how the debris impact one another, finite element is not able to do that because it's based on continuum, no? So we use ELS software from ASI International. You can Google it if you want. Thank you. So we can continue, Yannick?
Yes, I have two questions, one for Peter, one for Monica. From Peter, I want you to could you tell me what do you think about 3D printing?
They're facing also some challenges, I would say. And regarding the sustainability aspect, I see it from now a bit more critical. I think when
Why?
they become these challenges and they start printing more like with concrete and not mortar and having less cement, when the mixture gets more sustainable or less cement, I think it's an option for sure. And I think in the end it's nice to have a combination since it's you can use it in so many different ways, also for formwork or for structural building at least, but they have I think there are just a few more challenges they have to overcome, like reinforcement, etc., cracking,
Yes.
etc. But since then, I think the combination, we had some tests also going on a few years ago with 3D concrete printing.
Yes.
We used it more or less for formwork, but therefore the mixtures have just too much cement in there. But I think the combination in precast and with our production cell, we're building it. If you just get the 3D print head, we also use it at the moment also then for just filling our formwork with concrete. But if you adapt this, you can also do formwork or architectural design stuff. So using a 6X industrial robot gives you the opportunity, I think, to do several tasks as you want. And it's just by switching the print head or or a gripper, you place it on, it's super fast. You can do this automatically.
Because
so from this
now there's a lot of work around using earth for printing. Maybe it could be a sustainable solution.
This is super interesting, and I also have seen 3D printing with wax. So they 3D print wax, pure concrete in between, heat it up a bit, or then it melts, and you can reuse the wax again.
Yes.
There are super crazy ideas also with. I've seen ice drilled and milled, and then concrete poured in, and then when water melts, you have the structure of concrete.
Yes, that's interesting.
Yeah. And injection in sand and in other fluids, it's kind of interesting. But sure, there are challenges to be implemented, but can be done by the robot. But yeah, you have to be super specialized to operate these systems then.
Okay. And for Monica, it is just curiosity. I was wondering if the method you develop can be applied to structure Andre is working on. For example, to forecast if the part who did not collapse is still good.
You mean like the neural network model?
Yes.
These kind of models, machine learning techniques can be applied to any problem. So for sure, if we have like several simulations with different configurations of, for example, I could imagine like removing different elements in the building. We could use like a neural network model also to predict how it's going to fail, at least until what extent it could fail, like what area. Yeah, so it could be actually interesting to do something like that since Andrew is performing so many simulations, and it's also validated through experimental campaigns. So yes, I think it could be possible.
So for the method work, you need simulation about the structure. But Andre, did you simulate the safe part, no, the part which did not collapse? Are you able to tell if the part which did not collapse is still
Yes. Thanks, Yannick. So yeah, what totally agree with Monica said. I think we can adopt what is called probably like surrogate modeling, no, even for doing this. Yes, we measure the damage in the upright part, yeah, the part that survives. Now we are
yes?
actually working on this kind of framework, no? So we have different buildings with different position of segmentation, but also the impact of how after this failure happens, what happened to the rest of the building, no? So now we are defining some key parameters to measure the damage, no? Because you need to have some measurement, some quantities to measure the damage. For example, we use the residual drift. It's not usually used for progressive collapse, no, usually used for earthquake, but actually in our case it works quite well because if you know the peak drift and the residual drift, you know more or less the level of damage in your system, the residual drift, also the energy that you have in your system. And yeah, we are still working on it, but we are still far away from to developing like a design approach or an optimum design even of segmentation. We are still far below it. We are still like very low technical technology readiness level. We are very low TRL, just to let you know.
Okay. Okay, thank you for your answers.
Yeah. Another question from Baptiste Luzu. Yeah.
Yes, thank you for all the speakers. It was very, very interesting. My question is for you, Andre. Do you think that substituting reinforcing bars in concrete with metal fibers would allow for easier segmentation while ensuring the continuity of the building?
Very good point. So at that time, we actually considering this. We actually consider to replace some part of the rebar with um, non-metallic reinforcement, no? For example, with basalt or glass or so on. But yeah, the challenge is of course because this bar is very high in terms of strength, no, to my understanding, but can be very brittle. So this is the challenging part because sometimes in our system we want to have something brittle, but before it is triggered, you need to have a bit of ductility because you don't want to actually have a structure that is like a house of cards, we call it. Like you don't want to have a structure that is collapsed by just like a small wind loading, no? So the challenge here is actually to weaken your structure, but not too weak, but not too strong, right? So it is a possibility, I would say, to use other types of bars, for example, to create segmentation. There are many ways. There are many ways that you can achieve a segmentation. We are working on what we have now is we are using some modified mechanical rubber coupler, for example. We are working on this also, how to create like a fuse with mechanical coupler, for example, so that we can control the forces that is being transferred between bars. But yes, you can do with another type of bar.
Okay. Uh, but I wonder if substituting by metal fibers, because fibers in the concrete are well homogenized, reparted, and there is a good tensile strength, but the fibers are not connected each other. So maybe for the segmentation, it could be a good point.
I see what you mean. It's like distributed fiber, right? Like fiber
Yes.
FRC. Yeah,
Yes.
this is a possibility. Probably we can explore a bit also about this. We are still working on normal concrete, but there is a possibility, as you said, no, because it has a good tensile strength, it has some cracking control.
Yes.
Yeah, I mean, thanks for the suggestion. We are still designing our cast in situ building, so probably we can consider to use this also as a solution. FRC. Thank you very
Well,
much.
thank you for your answer.
I also have some questions for Monica and Peter. Okay, but probably for Monica first. I think the framework that you propose is very, very, very interesting and very relevant to our current challenges. No, my first question is about the input for the framework. No, how comprehensive or how detailed it is you need for example, the bridges. You need geometry. You need probably some information about the material properties, the traffic loading. Can you elaborate a bit more about the input that you use for this framework? And how sensitive it is to this.
Yes. So, well, as I said, I did not explain like the overall framework because it has too many components. So actually the inputs depend on each of them because, for example, if we talk about the Bayesian probabilistic modeling of the flooding event, it requires more like data regarding the precipitation for each of the return periods, and then you would require data regarding the soil conditions to know how is it going to so how the flood will evolve over time, and what would be the river velocity, the water depth, and all those hydraulic aspects. So those would be like the inputs for the part of the flood modeling. Then for the part of the fragility model, as you said, yes, you would need like the geometry of the bridges with like ideally you will need like all the detailed information about the bridges, but actually for my thesis we didn't have like so much detailed information. So what I did was to try to focus on the predominant failure modes and to try to categorize each bridge per bridge types and analyze for those bridge types what were the most relevant information to define the probability of failure for each intensity of the hazard. So yeah, indeed, the inputs that we need to perform this type of analysis are like a lot. It's very consuming, and sometimes the owners don't have this information because we are talking about infrastructures that were built like 50 or even 100 years ago. I had one of the case studies, it was like 110 years built. So it's very challenging to have all the information from them. So that's why also the taking into account all the uncertainties in these parameters is very relevant when we analyze the results of the risks estimates.
Okay. And another question for Monica. How would you extend, let's say, this framework to consider like multi-hazard problem, for example? What would be the plan going forward with the framework?
Well, for multi-hazard, for example, we are thinking and we are starting a work studying the combination of floods with earthquakes, in the sense of, for example, if you have a flood event and then you have some scour occurring on the foundations, and this reduces the stiffness of the foundation. And then if you have an earthquake, those foundations are more vulnerable to the effect of an earthquake.
Yeah.
So we are not considering like as simultaneously, but more like a cascading effect. So first we will have like the flood event that will leave the structure more vulnerable to the effect of an earthquake, for example. And this is the same case, for example, for wildfires. We have other studies that we've done in the group regarding the wildfires. And we know that, for example, after a wildfire, we lose a lot of vegetation, and then that changes some of the coefficients that will lead to an increase in the flood depth. So if we have a wildfire and then we have a flooding event or extreme precipitation event, we will have even higher flood depths and velocities and discharges of our bridges. So again, we have seen this from a more like a cascading effect of the multi-hazard more not like concurrent, even though concurrent can also happen, but we are thinking more on those critical cascading multi-hazard events.
Okay, perfect. Thank you very much for the answer, Monica.
Thank you, Andrew, for the
yeah,
question.
some question for Peter as well. When I did my postdoc in Switzerland, no, because here in Switzerland, there in Switzerland, they're working a lot with fabrication. They have the NCCR DFAB. I think you're familiar with what they're working
Yes.
on there. But I have some, I would say I'm a big fan of prefabrication. I'm a big fan of this modular system and 3D printing. But I always have a question about the potential scaling. No, if you have this, okay, this system works if you have a, let's say, of an infrastructure that is ready to do so. But at the same time, if you see the statistics, actually, most of the construction that are going on now is actually mostly in the developing countries, no? Because, for example, now in Europe, probably the majority of the buildings are there. So the question is more about aging and how to extend the service life. But the infrastructure boom is currently happening probably in Asia, in India, or in Africa at the same time. And which means that in these countries which require the solution, probably it's not directly applicable because, for example, in these countries probably we don't have robots, we don't have automation. So what is your vision of like how would you be able to scale the same framework to other parts of the world that the infrastructure is probably not as advanced as in Austria or Germany or Switzerland, for example? Just to give your opinion.
We thought about having a modular system so that the robot is in a container and then you add a second container maybe where all the other stuff is stored so that you can not kind of sell or ship this whole system with an operation center where you sit in there and operate everything and have it maybe also on site, also a robot. So you can, and regarding in case of sustainability, it would also better to produce them already on site. So you don't have to deliver these big beams or ceiling systems when you can produce them already on site. It's more sustainable. We had this circumstance also. I showed a picture about the used stock. So when we renovate our buildings, therefore individual shuttering and individual stuff you have to produce is increased since geometries are not like you planned it beforehand. So I think there could be the opportunity and possibility to use it and also on site. And for sure, in developing countries or countries that are just building more and more and more, there for sure you have to have everything packed in and give them the opportunity and the capability to produce it this way. And therefore you have to pack everything in you need for it and not just show them how it could be done and just I think that's the better way, I would say.
Very interesting point of view. I was also thinking about labor costs, no? Because yes, in Europe you can basically substitute manual labor with robot and you get some cost efficiency. But this is not always the case, no? Because in other countries probably substituting human with robots even costing more, and yes, the productivity is higher, but sometimes it's also difficult to convince people if there is no significant cost incentive also, no? So probably hybrid construction can be done also, no? I don't know, like combining printed formwork with some manual labors or something. Do you have some opinion on this also?
If you can just lend the system to a construction site, it would be also an opportunity. So you can have your manual on construction site casting concrete and add it up with the free prefab. So if there is no prefab nearby or even surrounding somewhere else, you could just deliver the fabrication on the construction site, how it's done in Europe mostly when you prepare a lot of concrete to construction site. You also build up. You see this sometimes when you go on highways. There are sometimes such mobile productions of concrete. When you add there 2 or 3 containers where you can do your precast, everything could also be an option, I would say. But that's big thinking, I would say.
Okay. Thank you, Peter. Joao, you have another question?
Not so much as a question, but also an observation, because there's also regarding automation, there's also another vector that has not been thought about yet when I think about motivations, or at least most. But I think it's a matter of time until some automated equipment becomes a standard equipment to be used at precast factories that do their regular job and even at construction sites. As
Yeah.
we have equipments for several purposes, these more detailed production processes that can be done with high geometric quality and aesthetics will become a regular tool.
Yeah,
I agree.
Buildings do not have to be fully automated.
for sure. So there's always, I think, a combination in ideas and how you build it up, since foundation will be also hard to precast to a certain point.
Yes,
Yes.
but one day we will get there.
One day, yeah.
Yeah. So is there any more question or discussion or opinion, for example, from the audience about the topic? We still have some time, I think, to discuss or how to connect between the dots of our research today. I don't know. I think.
I still have a question for you, Andre.
Sure, Monica, yes.
Yeah, regarding the part that you were saying about the double bars that they kind of activate when there is like this very high compression strength,
Yeah.
stress. So how does this happen exactly? How do they activate? I mean, do you have sensors or something embedded?
Yeah, no, actually, it's a bit like a passive fuse system, no? Basically, because in this precast, no, when you bend this system to transfer like hogging moment, for example, you have the tension in the top bar, and then you have all the compression goes to this dowel, no? So basically, if you adjust the dowel size, you can actually control the maximum bending moment or tensile force that you can transfer. So basically, you can just simply changing the dowel bar size in order to to adjust the bending moment that you can transfer. So at the moment we don't use any fancy measurement yet, but it's more about a philosophy of
Okay.
controlling the capacity and also the demand.
Okay.
Mhm.
No, because with all the discussions, I was thinking if it was not also like interesting to think about embedding also some sensors to do this activation, like depending on the where the failure occurs, some of them should segment and some others should not and should guarantee the continuity. I don't know, like because we are also working a lot with including sensors in our infrastructures. So I don't know if that could be interesting also to explore, like if another type of activating system could also work to decide between that segmentation and continuity based on the specific failure.
I mean, that would be very interesting. Yeah, I mean, yes, if you can have like a switch, no, even like a button that you can click and eject and the structure breaks. I mean, that will be the future, I would say, because as I said before, no, the work that we are working on now is very fundamental. So when my professor say what is the objective of this project, he says, okay, we want to break or segment the buildings when we want. That's the only thing that we want to achieve at the moment. But of course, if we have even more control on exactly which part that we allow to break and when it breaks, how it breaks. That's even much better, yeah. Because now we have a lot of smart materials. No, I think we have some like shape memory alloy, for example, that you can control with some temperature or something. Probably, uh, yeah. But I would love to explore this kind of opportunity. Yeah. So if you guys have some ideas or collaboration, I can speak with my professor to probably work on proof of concept because we in this ERC grant you can have two proof of concept. We have applied one that is for precast system, but if you have some ideas and your team wants to collaborate or something, we are still open also to work on another proof of concept.
Okay.
But thank you, Monica, for that's. I will speak with my professor to see his opinion also. Thank you.
Okay.
Do we have more questions? I think we can close in 4:45 or 4:50. So we can have one more. Yannick, you have something?
No, I wanted to ask, what do you plan to discuss in the in-person? Do you have idea on how yours or our different works could get together, or what is your idea for the future, no,
Yeah,
collaborations?
for the session in Nice, no? In the during the day of
Yes,
the
in person
conference, yeah,
or
in
for
person.
futures meeting.
What do you think, Yannick? I mean, you're the organizer, so you
No,
you you
is
can decide.
yes.
I follow you. What do
No,
you want?
it's yeah, yes, of course. My question was not about organization. It's
Mhm.
about the questions of the meeting of today is how resilience and sustainability can go together. For
Yeah.
conclusion of this session,
Okay.
what can you tell according to you?
Okay. Probably Peter and Monica also have something to say, but from my side, I think the answer is yes, it's possible.
Yes,
Yes, it's possible. So you can have a structure that is resilient but also sustainable. The question is how.
yes, how?
I think the question is how. So yeah, combining what of the work that we are working on, no, like with prefab, with integration of risk analysis, but also new philosophy. I think new structural design philosophy, and um, yeah, more, let's say, holistic perspective, no, because probably the perspective that
Exactly,
we are working on now is usually fragmented. Okay,
exactly,
clients want to have everything cheap. Engineer wants
exactly.
to have everything easy to build, and then I don't know, environmentalist wants everything to be as environmentally friendly as possible. But the
Yes,
question is how to have a holistic framework that
yes.
can not compensate, but integrate and harmonize all of them. So that's the question. It's more about the framework of thinking, I would say, Yannick.
Okay,
I
so
would totally agree on that, I would say. And there are so many aspects for the holistic view. And then comes also in hand that if you have a sustainable building, there are clients living in there or companies living in there, but the owner is probably someone else and he wants to have it cheap
Mhm.
or more cheap. And this also sometimes is not the best way to build, I would say.
Yeah, yeah. Um,
how do we do an holistic view of construction? This is the question we will try to answer.
I mean, there are many possibilities, no? But I think one that has been quite widely used is performance-based framework, no? Basically, you depends on what buildings you are working on. You set a
Ah,
specific
yes.
objective based
Mhm.
on the client's demand and risk profile, and also performing some loss analysis and including probably life cycle costs. So within this
Exactly.
performance-based framework, I think you can include everything in the framework. But of
But
course, still it's challenging.
from now, the LCA is not included in the performance-based approach, only durability. I don't
Mhm.
know if you have already see the study with LCA approach in performance-based.
I've seen this one. I think this was from Michael Heist and Konrad Bergmeister was their idea a few years ago to design or have a code design based on LCA. So you design
Okay.
based on your outcome on the LCA for the structure, but it's also a bit critical scene. So there's also a lot of work to do, what I've heard so far.
Yeah.
But there is an approach that this is also a design or a code how you can design and
Yes.
tell afterwards which design fits best, and that's based on LCA.
Yes.
Okay.
I agree with Peter. What we use, for example, in our research, we don't consider LCA explicitly, but in the consequence analysis, no? For example, if we consider a building collapse, we consider also the cost of CO2 that you need to spend to replace the building. So you can
Mm.
consider this in the cost benefit in a way. Of
Okay.
course, it's not a comprehensive life cycle because we just consider specifically okay, if this part collapse, how to rebuild this, you would need some CO2, and then this is considering how much it costs. Also, the fatalities we consider usually like what Monica used in the framework, the same like casualties, environmental impact, and also the direct cost impact, for example. I think this is
Okay.
where you can include the LCA also.
Okay.
Yeah, and the resilience part is also embedded in all that Andre and Peter presented, because like increasing the robustness directly increases the resilience. And also if we introduce some of the concepts that Peter introduced for the recovery part, like for the
Yeah.
reconstruction and the automation, we are also increasing the recovery part of the resilience and the rapidity and the resourcefulness of the resilience. So yeah, I think it can be all of it holistically integrated.
Okay.
Probably resilience-based design will be the future, yeah.
Mhm.
Yes, yes, very good idea. Resilient-based design.
To consider also recovery time and everything, no, after the hazards and the importance of maintenance within also, so you have one framework that accounts for everything that happens during the service life.
I think that we should create a project around resilient-based design of structure. This is very interesting idea.
Probably a concept first, no? I would say
Yes,
even a concept first, how to define it for a practical design approach, for example.
this is very interesting.
Because can I ask you, Monica, for this framework, usually it's for assessment, right? Am I right? When you use
It's
this
for
risk
assessment,
analysis? Yeah.
yeah, and management as well. I mean, the final part, it's like decision making. So to decide where to invest, which structures to prioritize and maintain first, or which ones we need to replace.
Yes,
Yeah.
exactly. It's for existing facilities, no? Usually.
Yeah, it's more, we have applied more for management of existing infrastructures.
Mhm.
But it can also be applied for deciding on the reliability level of new structures as well, like how we
Okay.
want what is the our goal at the network level for our infrastructures to behave.
I see. Very interesting. Thank you very much, everyone, for the very fruitful, let's say, brainstorming and discussion session today. Yeah, I think we already discussed like many different things, many different advances in different fronts of research. And of course, there are still more things to do and more things to probably integrate between different aspects in our field, no? So thank you very much for today.